thank you so much for joining this afternoon's verbal presentations. We're here today to hear about monitoring and evaluation from different perspectives. Our first presentation is from Mahboobeh from University of Illinois, Chicago, discussing today the evaluation of a fluorescence-based sensor for simultaneous measurement of E. coli and turbidity in water. Please welcome. If you'd like the clicker, it's ready for you.
Okay. Hello everyone, my name is Kasraee. I'm a PhD student at the School of Public Health, University of Illinois, Chicago. And today I'm going to present our collaborative work with Photon Research Institute on evaluation of a fluorescence-based sensor for simultaneous measurements of E. coli and turbidity in beach water. As you all know, conventional lab-based methods for monitoring recreational water quality usually require 18 to 24 hours for culture or 5 hours for qPCR methods, which leads to late advisory. That means that public warning for potential contamination in beach water is often delayed. And it also needs steril conditions and trained staff, while sensor-based methods gives us real-time output within seconds to minutes. So it enables a near-instant advisory, so public warning would be released very soon. They are field deployable, and there is no need for laboratory equipment or trained staff. The sensor was developed by engineers in Photon Research Institute in Nepal, and you can see the picture of the sensor is about the size of a box of napkin, and it completely can be fitted in a backpack. The sensor is capable of providing information about tryptophan-like fluorescence known as TLF, which correlates with E. coli levels in water, humic-like fluorescence known as HLF, and turbidity. The sensor uses the excitation wavelength of 280 nanometer and emission wavelength of 350 nanometer for detecting TLF signals. It's also worth to mention that signal can be impacted by matrix interferences like turbidity in water or non-microbial background fluorescence. The main purpose of our study was to evaluate the performance of the sensor and predicting the exceedance of EPA's beach action value for E. coli, which is 235 mpm per 100 milliliter. And then we aim to characterize relationship between TLF and E. coli culture. And then because several past studies raised question about where the TLF signals are coming from, whether they are extracellular or intracellular. So we aim to examine the effect of filtration on TLF signals. First of all, we started with sensor calibration. The sensor has 2-point calibration, 0 and 125. And it has 3 different channels. For each channel, we used a stock standard solution. We used tryptophan solution for calibrating TLF channel, quinine for HLF channel, and formazine for turbidity. And then to check the accuracy of the sensor reading, we prepared 12 different serial dilutions, starting from 1000, going down to almost 1, and then check the sensor readings with the known concentration of our dilutions. For sample collection, we chose 3 different beaches across Chicago: Montrose Beach, Calumet Beach, and Ohio Street Beach. Sampling continued for 22 days, and in total we collected 66 samples. Sampling were done from 2 different transects of each beach. Sample volume was 1 liter for each transect at each beach, and then later composited in the lab and then analyzed within 2 hours of collection. In lab, we went through 2 different steps. for processing the sample. For pure filtration, we used raw with water sample and then pour it into quantity tray. For colilert culture, we took 3 milliliter of the sample for reading by a spectrophotometer, turbidimeter, and 4 milliliter of the sample for reading by the sensor. And then the remaining volume of the sample went through filtration using 0.22 micrometer filters, and then the filtered sample went through colilert culture and reading by the turbidimeter and the sensor. For quality control, we included blank samples, and sensor measurements were done in triplicates, and colilert culture were done in duplicates. Here you can see the results of serial dilutions for checking the accuracy of the sensor after calibration, and you can see in the table the R-square values of each sensor readings. As you can see, there was almost perfect correlation between turbidity against its gold standards and TLF against colilert, while the correlation was big for HLF signals and TLF signal against the gold standard. Here in this picture you can see the beach action value exceedances per each beach. California had the highest number of exceedances and Ohio had the lowest number of exceedances, and in total 24% of samples exceeded EPA beach action value. And then here you can see the effect of filtration on TLF intensity. As you can see, TLF intensity obviously decreased after filtration. The mean of unfiltered samples were 90, but it decreased to 42 ppb after filtration. Because the TLF decreased but wasn't eliminated, so it suggests that TLF signals, some of the TLF signals come from inside of the bacteria cells, and some of them are coming from the beach water, and they are extracellular. And then we applied single predictor analysis beach action value exceedance separately for filtered and unfiltered TLF. As you can see in the first table, unfiltered TLF showed a significant association with E.coli beach action value exceedance with odds ratio of 1.14, which is not a very high odds ratio. And then we applied multivariate analysis for beach action value exceedance, entering all variables into the model. Again, you can see in the second table that TLF was the only significant predictor for E.coli beach action value exceedance, with only 20% increase in odds of BAV exceedance. Then we looked for sensitivity and specificity of the sensor in beach-specific models, and you can see that Ohio and California showed the highest sensitivity, and overall the sensitivity was good and the specificity was moderate. And then in pooled model, the sensor had a variability in how well the sensor performed. As you can see, Ohio was neither sensitive nor specific, but two other beaches and the pool results show high sensitivity and fair specificity. As a conclusion, after filtration, we had decrease in our TLF signals, so we can conclude that TLF signals are partly extracellular and intracellular, and TLF was found to be the only predictor of E.coli beach action value exceedance. As we had a good sensitivity and moderate specificity in our study setting, we can say that the sensor showed the potential to predict beach action value in near real time. But also it's important to say that our study was a small study. We only collected sample for 22 days, and we only tested the sensor for a single freshwater lake in Lake Michigan. Also, in future, there is need to evaluate the sensor in different locations and under different weathers, and it's better to test the sensor in marine beaches. And as the sensor showed the potential for testing the drinking water, so we can evaluate drinking water in low-income countries. If you have any question regarding the device, you can email to this, and here are the references. Now I'm happy to answer any of your questions.
Sure. You don't mind? Any questions? Okay, I have a question. So your sensitivity and specificity were in relation to the IDEX results. Have you been able to look back at any sensitivity or specificity estimates for IDEX itself?
For IDEX, we didn't do that separately. It was just, yeah.
And then I'm wondering if there might be some way to implement that in your analyses too, because I imagine that the IDEX media itself is not 100% specific, and so if there might be a way to implement that into your calculations. Are there other questions? Yeah, Timothy.
Hey, Timothy Burgess here. Great presentation. Love to hear about TLF at Water and Health. A question about it, because I've done some TLF work in the past, and I was wondering for some of your methods, when you sampled the beaches, were you taking like repeat measurements at the same location? I'm wondering how much variability there is if you may have measured taking measurements at the same location at the same time.
So we did readings triplicates, and then we analyzed the precision of the readings using coefficient variance, and most of them were below 10%. Only for each beaches, only 10 to 12 samples were above 10%. So I think it was not.
Okay, to clarify, that's measurement triplicate, not sampling triplicate, correct?
Yeah, measurements by the sensor was triplicate. Yeah.
Okay, I think it would be interesting to also see in some of the follow-up studies, as you've mentioned, of testing out some of the other specs on it, how much variability there is in the same site, because I found that with some other system types of seeing a lot of variability within measurements taken one after another in the same kind of background matrix. So that's a question I haven't heard necessarily answered by TLF in general, so I'd love to hear more about that at next year's conference for me. Yeah.
Is there any other questions? Yeah.
So could we use this method for other environmental samples which are potentially more contaminated, probably with sewage or something? Would there be like change in baseline threshold for other noises from other sources with this reused in those?
I think there would be lots of background noises if we wanted to test it with sewage, but we are still learning from the sensor. Maybe we need to go for further investigation. So maybe it would be perfect for them. I don't know.
Thank you.
Maybe last question, so we still have like 1 to 2 minutes from this first session. Okay, so
With that, thank you so much.
thank you so much.
up Clay Burgess, who is a consultant with AECOM right now, but is also consulting with the Water Institute at UNC, and he'll provide an overview of his systematic review of toxic metals exposures through drinking water in Africa. So Clay, if you want to come join me, I'm getting your presentation up.
All right. Hi, everybody. My name is Clay Burgess. I work with AECOM, and I've also been involved with some work with the Water Institute here at UNC. And so I've had the opportunity to work with a handful of collaborators on our project, a systematic review of toxic metals exposures through drinking water in East Africa. This project stems from a larger systematic review on all low and middle income countries that is currently being done by Dr. Mike Fisher. And this work has been supported by USAID through the GH Pearl program. So toxic metals can produce a variety of negative health effects. These include things like cardiovascular disease, neurological damage, and cancer, among other health impacts. Exposure can occur through water, food, soil, inhalation, among other routes. Toxic metals in drinking water can be derived from multiple sources. They can occur through anthropogenic contamination, which is human activity, geogenic, which is naturally occurring, or they can be water system derived. So that's where they leach from water system parts. So one example of a water system derived and anthropogenic contaminant is lead, which has a WHO guideline value of 10 parts per billion in drinking water. Manganese is an example of a geogenic contaminant, and the WHO guideline value there is 80 parts per billion. Water is an important route of exposure to toxic metals. This can occur through bathing, drinking, or cooking. The negative impacts of exposure can compound over time, so intervening early is key. Water system corrosion dominates waterborne lead contamination, and anthropogenic toxic metal sources contaminate water systems at any point of interaction, while geogenic toxic metals contaminate groundwater. The exposure to toxic metals in East Africa is not adequately synthesized in current data, and this may be due to gaps in data as well as inadequate documentation of the methods used. Additionally, the data availability does not always align with the population density of the region. But one reason we did choose East Africa for this smaller subset of data that we're focused on is that there is some data compared to Africa as a whole. When I say East Africa, I'm referring specifically to Ethiopia, Kenya, Uganda, and Tanzania. Another reason that we chose this region is that they are making advancements towards trying to reduce exposures to toxic metals. And so that's one example of that would be that Uganda is a founding partner of the Global Lead-Free Water Pledge. The majority of this region relies on improved sources of drinking water. And one thing to note with toxic metal exposures is that improved sources are not necessarily more safe from contamination than unimproved sources. About 25% of this population uses piped water, and there's limited access to highly sensitive instruments, like an ICP-MS in this region. And highly sensitive instrumentation is important for measuring toxic metals because some metals like lead can cause health effects at very low concentrations, so you need this highly sensitive equipment to measure for it, but it is expensive. So our objectives are to understand where toxic metals are occurring in East Africa and whether they're exceeding WHO guideline values, and to identify gaps in current data to help improve decision making. So for the largest systematic review, we've conducted a search across major literature databases, and we're looking for peer-reviewed papers published after 1969 in English, reporting on primary data in drinking water. And for this project, we're looking specifically at lead and manganese. And as I've mentioned, our countries of interest are Uganda, Kenya, Tanzania, and Ethiopia. Now we can jump into the results. So the first thing to notice here is that we're seeing a lot more data from Ethiopia than we are from Kenya and from Tanzania and Uganda, which we'll get to on the next slide. So many more studies as well as total observations. We had a good split of data between improved and unimproved sources for both metals in Ethiopia. Another thing to notice here is that we have a lot more data for manganese than lead, and this may be because manganese doesn't require that highly sensitive instrumentation, as I mentioned before. Additionally, if you look here at observations of lead and improved sources in Kenya, you can see we only have 38 observations, so we're already starting to see where there's some limitations in this data. And continuing on with Tanzania and Uganda, very low number total of observations compared to the data we have from Ethiopia. And here with manganese and observations in unimproved sources from Uganda, again, only 21 observations. So we can see this limited data is occurring in both metals and across both improved and unimproved source types. So we had 2,894 total observations for manganese, which is many more than we had for lead. The WHO guideline value, as I mentioned before, is 80 parts per billion, and we were seeing roughly 52% of observations exceeding the WHO guideline value in this region. One thing to note is, this is based on very limited data, so this is by no means a definitive, like this is the exceedance we're seeing in this region for manganese, but it is pretty high, and it does cause, it does kind of raise some concerns about there may need to be some next steps here. And then you can see, looking at this map, geographically where we have lots of gaps in the data, so like here in the central part of Kenya, lots of Tanzania down here, only a few observations from Uganda. Additionally, we're seeing a lot more observations exceeding the WHO guideline value in improved sources compared to unimproved sources at 63% compared to 44%. And this may be due to the fact that manganese is a geogenic contaminant. So when you're using improved sources to get water from an aquifer, for example, the water there may be in contact with bedrock that contains manganese. For lead, we had 1,961 total observations, and we were seeing an exceedance around 33%. So again, looking at this map, you can see where it's even more limited for lead than it is for manganese. And here in Ethiopia, most of the data is clustered centrally, limited data from Tanzania. So again, just a lack of geographic coverage of the region. In the literature for improved sources, it did seem to be referencing lead-containing infrastructure as a common contaminant for improved sources, and then for unimproved sources in the literature, we were seeing industrial waste. So as I've mentioned, the data we have here is very limited. Geographically, it doesn't cover the map very well, but what we are seeing is there is some concern for both manganese and lead. We're seeing relatively high exceedances. So now we can kind of move into what does this data mean. So for both manganese and lead, over 30% of observations were exceeding the WHO guideline values in both improved and unimproved sources. As I've mentioned, the data does not necessarily geographically represent this region very well. Looking at that map to the right, those colored in either sub-counties or districts represent ones from which we had data. Many urban areas are not covered well in this data set, but despite this, some trends may be identified. As I mentioned, manganese, we were seeing higher exceedance in improved sources compared to unimproved sources, possibly due to the fact that it's geogenic. And with lead, lead-containing infrastructure was oftentimes referenced in the literature as contaminating improved sources. Looking down at this table here, you can see at best our data was covering 5.7% of Ethiopia's population, and roughly 3 to 4% of Kenya, Uganda, and Tanzania's. And looking through the literature for Ethiopia, we did notice that the papers would reference the use of an ICP-MS in country, and that was not something we were seeing for the other countries. So when you're seeing exposures to toxic metals, there's typically two strategies for intervention. That would be prevention and remediation. Typically, remediation and prevention strategies for manganese are moderate or relatively high cost, but one thing that stands out here is that prevention for lead is a relatively low cost intervention. As we're seeing from a recent study that only 2% installation costs, and so this intervention involves, as new water systems are developed, changing the supply chain from lead canning to lead-free infrastructure. Another kind of no regrets strategy we're seeing here would be, has to do with the need for data in this region. So collecting more data, and particularly high quality data, helps determine what intervention will have the highest impact and where this intervention needs to go. So the major takeaways from this work so far would be that across the region for both manganese and lead, in improved as well as unimproved source types, we were seeing over 30% observations exceeding the WHO guideline values for both of these metals. There's major gaps in our current data. As you can see, at best, only 4 to 6% of each country's population is represented, which is why there's a need for collecting more data, particularly high quality data, as this could help in decision making. Additionally, a no regrets intervention exists for lead, and that has to do with the selection of lead-free parts in new water systems. So some next steps for this work include geostatistical analyses, trend analysis, and comparison of possible industrial sources. So I want to thank all of the collaborators on this work. You can see it's a lot of people. I know some of them are here in the room, and some of them may be joining online from our Ghana team. So thank you to everybody, and thank you all for listening, and I'd be happy to take any questions.
Questions for Clay?
Questions?
Thank you. You mentioned that more data is going to be really helpful. Do you have any suggestions after sifting through all of this and trying to find it about where those data should come from and where you think you could maybe even influence future regular collection of these data?
Yeah. Yeah. So that's a tough question. This
Sorry.
is that's okay. It's just there's so much data like we've already had to go through, and so I'm trying to figure out where next data should go. But I think one thing is urban areas, more urban representation in this data set. So like a lot of the major cities across all 4 countries, we would have like only one study there, or some studies we were like in Tanzania. I don't think we had any data from Dar es Salaam, their not their capital, but their largest city. So yeah, urban areas, cities, we need more data for.
Next question.
Hi, really interesting findings. I'm wondering, lead is pervasive in the environment and can be a difficulty to not include in your samples or even in your lab equipment. I'm wondering if you found anything in these papers related to the quality assurance for lead sampling and analysis in this region.
Yes, so as part of our process, our systematic review process, we did try to look at QA/QC measures in the studies we're looking at. So we have collected information on that, but I honestly haven't dove into that. But that's something that would be interesting to look more into, and yeah, I'd be happy to talk more about that after this, and we can pull up the data. But yeah, I couldn't tell you right now.
We have time for one more question.
I would
I was trying to formulate a question around something, and I read a bullet point, and I see up there that some information may be under government-owned water quality monitoring data. So I'm just wondering if you or any colleagues have explored that. I mean, you're acknowledging it's there. Do you have any idea of how much additional data is there? And also, maybe piggyback on that, I don't know anything about modeling this kind of data, but, with a little bit of data, could you do something to kind of, you said geostatistical analysis, what would that look like, and how much more data do you need to be able to do something, an effective method in terms of modeling?
So, in regards to the first question, I'm not sure how much gray literature and government-owned stuff there is out there. I think I believe there probably is a decent amount, but I don't want to comment. I don't know the extent that well. I know some of the people who have worked on this project are here in the room. I don't know if any of you guys can jump in if you have any insight, but
Yeah, go
Jump in real quick.
yeah.
Sorry, I've also been working on the systematic review, actually looking at some of the gray literature. I think Clay had mentioned this earlier. One of the issues that we're running into is on the QA/QC side, we're trying to guarantee that it's using adequate instrumentation. If you have something that reports, it's less than 40 parts per billion for lead, what does that actually mean? So a lot of the record keeping isn't necessarily great for integrating into the current data set, especially when there's not identified ICP-MS usage that gets down to really sensitive data.
Thank you. Another round of applause for Jeff, please. All right, and next up, I'm excited to introduce an undergraduate researcher, Charlotte Smart, who is joining us from Fort Lewis College. Okay, and again, we're welcoming Charlotte Smart, who is an undergraduate researcher at St. Louis College. Thanks.
Hi everyone, my name is Charlotte Smart. I'm an undergraduate student at Fort Lewis College. Thanks for coming to my presentation on improving water quality data by optimizing CompactDry ECO plate use, which is a research project we carried out with University of Victoria. So just a bit of background, this map shows the proportion of population that has access to safely managed drinking water services. Now, something you might notice on this map is that there is a lot of gray, and those are places where there is insufficient data to make an estimate on safely managed drinking water percentages. And the main limiter for safely managed drinking water is water quality data. So in the context of the JMP, that usually means fecal contamination or E. coli. And so this map is actually a big improvement over previous years. So the previous JMP report had about 50% of the world covered by their data, and this new JMP report has about 70% of the world covered with their data. And that is in large part due to MIX, which uses a membrane filtration technique to quantify E. coli out in the field. It's had several adaptations made to it to make it more usable in the field, one of which we're going to focus on today, which are these CompactDry plates, which are a type of dehydrated nutrient media that you can add a milliliter of water to and incubate it. So UNICEF has adapted this so that they rehydrate it with a milliliter of water and then add a membrane filter before incubating. but there have been some challenges associated with using these plates. The first of which is excess water from rehydration has led to smearing of some of those E. coli colonies after incubation, leading to trouble with quantifying the samples, which leads to our first research question, which is what rehydration volume produces smearing with no loss of accuracy, or produces no smearing without loss of accuracy. So the second challenge that has been run into is the relatively short shelf life of these plates. You know, surveys often get delayed and the plates expire, causing further delays. And so that brings us to our second research question, which is, does using these expired plates actually pose a significant potential to change the WHO risk category of a sample? So moving on to our the rehydration study, we answered this question by doing 6 membrane filtrations, either using an easy fit manifold, which is kind of more typically seen within laboratory settings, or using these affordable JMP designed 2-gland manifolds, which I have one right here. And we looked at those just because there were some questions on whether or not they might add extra water to the membrane filters. From there, we took those membrane filters and plated them onto CompactDry plates that had been rehydrated either with the 1 milliliter, which is the UNICEF standard, or an alternate rehydration volume, which is ranging from 0.4 to 0.8 milliliters. We didn't include 0.9 just because of some preliminary testing. From there, we incubated either with an electric incubator, which again is typically seen in laboratory settings, or with an incubation belt, which, as was noted by one of the JMP consultants we were talking with, Sabor, they can have a little bit more variable temperatures, sometimes lower temperatures, since they rely on body heat. From there, we counted the plates and then categorized them. The first category are these readable plates, where there are these really nice, clear, defined countable dots, making quantification really easy. The second category are these semi-smeared plates, so you can see there's a little bit more distortion there that makes quantification a little bit harder, but you can still be reasonably certain that you're counting correctly. And then the final categorization are these smeared plates, where there's so much distortion, so much smearing, that you really have no idea what the concentration of E. coli is in that sample. So moving on to the results, as we expected, as the rehydration volume increased, so did the amount of smearing. Something that was interesting that we found was that when we separated out the samples by incubator, we found that there was a lot more smearing that happened with the electric incubator. And we think that's because of those higher, more consistent temperatures, with the incubator potentially causing more condensation on the plates, maybe altering some way of how the E. coli are growing. Either way, at this point it looks like 0.4 milliliters is ideal, since it has the least amount of smearing. But we also want to make sure we're not impacting the accuracy of our counts when using a reduced rehydration volume. So we did some statistical analyses. We first did a Friedman test on readable and semi-smeared plates, which is similar to an ANOVA test. And then we followed that up with a Dunn-Bonferroni post-hoc test to find where some of those significant differences were. We found that 0.4 milliliters was significantly different from 0.6 and 0.7 milliliters. Something that was interesting that came up from this is that 0.4 wasn't significantly different from 1 milliliter. And so we were a little confused by that, because we expected there to be some significant difference between the standard and whatever that lowest value was. So we ended up looking at and visualizing some of this data. So you'll see here on this graph, the x-axis is the counts that we got from the 1 milliliter plates comparing to the alternate volumes counts, or for colonies. So you'll notice that this green line, which represents the linear regression for the 0.4 plates, is under that dashed line that represents the perfect agreement between 1 milliliter plates, which that means that 0.4 is underestimating the concentration of E. coli when it's being used. Now, something else that's interesting is that these purple and orange lines here represent the 0.6 and 0.7 trials, and those are actually slightly above that perfect agreement with the standard. And so we think that because there are more semi-smeared plates among the 1 milliliters plates that we used, that we were actually conservatively counting some of those smears, leading to us underestimating the concentration of E. coli when using that standard 1 milliliter value. So at this point, it might seem that 0.5 is ideal since it has the least amount of smearing and there's no significant differences. But we realize things aren't ideal out in the field, so we're recommending 0.6 milliliters for a rehydration volume. There's one potential cause that we identified. These membrane filters can hold about 0.25 milliliters of water in them. We also recognize that 0.7 and 0.8 weren't ideal, so we think there's some other unknown factor at play, potentially with the membrane surface being a little bit slicker, causing more smearing. Moving on to the expired plate study, there's an initial study done by Rachel Boyer and Caetano Doria up at University of Victoria where they did 120 paired samples, plating onto expired plates and non-expired plates. And there were some results that looked promising, but there was some uncertainty in there because of some intrasample variance. And so we did a follow-up kind of batch trial study where we directly dispensed a milliliter of water onto 12 expired plates and 12 non-expired plates. For the paired samples, you'll see here this is comparing the the non-expired plates to the expired plates, and you'll see there's pretty good correlation with a Pearson correlation coefficient of 0.969, but there were some significant differences when a Wilcoxon signed rank test was performed, both for plate counts and for how the plates were categorized into WHO risk categories. And we think that this is because of some intrasample variance. So you'll notice that the data trends along this line, but it's pretty widely spread out across it. And that's that intrasample variance that we think are causing some of those significant differences to appear. So for the batch trial, here is so this is a box plot showing the different trials. The different colors represent the different trials. The darker color is the non-expired plates. The expired plates are the lighter colors. You'll see there's pretty good overlap. And crucially, we didn't find any significant differences, so we concluded that the expired plates are reliable up to 4 years past the expiration date. So for the rehydration study, again, just to reiterate, we recommended 0.6 milliliters. And the initial findings from that study have actually already impacted mix protocols. They reduced from recommending 1 milliliter down to recommending 0.8 to 1 milliliter. But we're hoping that our new findings can justify even further reductions of that rehydration volume. For the expired plate study, it was already used to justify some data that had been taken in Malawi that was taken with expired plates. And then there's also a survey happening in Panama right now that has been getting delayed for a long time, and the plates that they had were about to expire, and we were able to tell them that they could take their time with the survey instead of rushing through it or delaying it. So yeah, here's a bunch of people who helped out. Yeah, and thank you. Any questions?
First question.
Thank you so much. Congratulations. This research is wonderful. I was curious if you have any projections or insights into the variability within this test itself. I do some research using call alert tests and membrane filtration for E. coli enumeration, and just curious if you have any insights on, what the individual error is within these tests that might cause some variability in the results. Thank you.
Yeah, so for the expired plates, we actually compared them to some other research and literature, and we found that the coefficient of variation for the log counts is roughly within this order of magnitude of around that like 50%. It kind of depends on like how the concentration of your sample. The limit of detection is 1 CFU, and that kind of limits that coefficient of variation. I don't know, it's hard to say because it changes depending on the concentration. I will say that there is more noise typically in your results at the lower end because of that limit of detection, and I think that's probably where you have to be the most careful with interpreting results, because at a certain point, if you get 120 colonies on a plate versus 121, I don't know how much that matters.
Absolutely.
Yeah, so, yeah.
Thank you.
Next question. You have 2 more questions. Maybe
Thanks. I also have a question about concentration. Maybe I missed it, but when you were doing the work to justify using like 0.4 mil versus 0.6 versus 1, what concentration were you using during that? Because I can see, like, if we're talking about drinking water, right, you're talking about pretty low levels of E. coli and the heterogeneity there. Like, the less we're using the plate, maybe we're gonna miss something.
Yeah, so we primarily used expired plates, environmental samples. Oh man. Yeah, so we, for the most part, used environmental samples, but we did have to spike into some of those samples just so that we could get things in the higher and like very high WHO risk categories. But I think we have about, in total, for our entire data set, we had, I think 30 samples was what we were aiming for in each of the WHO risk categories. There were some tricky things with getting data sets that we could use for this Friedman test, which requires readable samples, or at least countable samples in each of the groups, the like 0.4 to 1 milliliters. And it's just a lot harder to get those at the higher concentrations because there's just, the smearing kind of makes that a lot harder to quantify, so.
Thanks.
Yeah.
Thanks for the very practical and clear presentation.
Thanks.
My question is about the expiration dates, and did you look at storage temperatures? Because I've used these plates and we've stored them, I think, above the recommended temperature, but always wondered if that's a problem.
Yeah, definitely.
Yeah, so I wouldn't be able to say if storing them in non-ideal temperatures would necessarily affect it. The plates that we use were stored in a cool, dark place, but at one point they were in a basement that got flooded with a bunch of water. And they worked fine, so yeah, but I don't know if I could say whether increased temperatures would impact that, so.
All right, one more round of applause. Thank you so much.
Right, next we'll welcome up Dr. Joseph Eisenberg from the University of Michigan, who will present to us. He and his students study on measuring E. coli in drinking water in low resource settings and balancing precision and sample size. Thanks.
Thank you. Probably more importantly than who I am, also who I'm not. I'm not Andrea Sosa, who is listed in the program. She's did this work for her PhD. Unfortunately, she couldn't make it here, so I'm the messenger of her great work. This work kind of started and was inspired by the work that we've been doing for a couple decades in low resource settings in rural Ecuador, where we needed to look for appropriate ways to measure water quality. And so wanted to look at the balance between higher cost, more precise continuous measures and lower cost measures, and look at that from a statistical perspective. I think our previous speaker provided this nice introduction for me, so it saves me a bit of time. I think I have 72%. You said 70%, so we're pretty close on that. I think that the point here is our interest is moving more and more toward more direct measure of exposure. We want to measure water quality, not just use proxies for measures, and it's important to have more data available, and lower cost methods are going to be more valuable there. And so just a little bit more specifics on that. When I'm talking about higher precision methods, again, I'm talking about fecal indicator measures. I know that there's more and more research done on measuring pathogens, which is great. It's getting cheaper and cheaper, but again, for low resource settings, that's not really practical. So we've got these higher precision measures that give us continuous measures, the IDEX membrane filtration. And then we have what I call lower precision methods that give us categorical information. We've got the presence-absence. We've got different ways in which to get various categorical ranges of measures of contamination. And the goal here is to compare these statistically, with the idea that using these categorical measures may reduce statistical power. So to do this, we took advantage of the mixed data set, which also our previous speaker did a nice job in introducing that to everybody. We used a sixth wave of data collection between 2016 and 2022. And what we did with that data is we basically emulated these lower precision measures. So in this case, emulated a two-category presence-absence, where we can measure less than 1 CFU per 100 mils or greater than, and that tracks on the WHO risk measures of either acceptable or anywhere from low to high. We've been experimenting using a combination of the presence-absence with there we go. Presence-absence with the petrifilm to give us an additional category of acceptable, low, intermediate to high. Importantly, since the membrane filtration approach has a limit of 100 CFU per 100 mils, our categorical approach, which actually gives us a little bit more fidelity in the high end, is, for this analysis, we're just considering all those categories as high. And this gives a little bit more detail about how this combination of presence-absence, petrifilm, can give us these 5 categories: acceptable, low, intermediate, high, very high, and extremely high. Again, we're collapsing the last 3 categories for this analysis. And then we emulate a compartment bag method where we can get 4 risk categories: acceptable, low, intermediate, and high, and use that as a way to, again, compare a bag test method to a more continuous membrane filtration method. So our goal here was to evaluate statistical power. The way we did that was we took two different exposure variables, water treatment and storage. And we wanted to look at the power and the sample size required to get an 80% power on this relationship. So we looked at the mixed data set, we found 11 countries that had satisfied our inclusion criteria of at least 3,000 water quality measurements, and included the question about water treatment and water storage. In this presentation, I'm going to only show the water treatment analysis. So we basically looked at the association between water quality measures and water treatment using logistic regression models. And again, we estimated the sample size needed to reach 80% power for detecting statistically significant differences using a bootstrap-based algorithm. So these are the 11 countries, and this is the data, the water quality data. The x-axis is CFU per 100 mil of E. coli. The range is from 0 to 100 CFU, and this is just showing the frequency. And we've got our 11 countries, and they're basically range in water quality. So we've got countries like Algeria, which has good water quality. Most of the samples are actually non-detect. And in comparison with Madagascar, we have an example of poor water quality where most of the samples are beyond the detection limit, too numerous to count. And so what I'm going to summarize is the results that we had for those countries with better water quality versus those, and then looked at those countries with poor water quality. So what we have here is basically the sample size ratio to reach 80% power. So, for example, a 1.9 for the presence-absent test means that the presence-absent test required 90% greater, 1.9 times more greater sample size than the membrane filtration. So, if we look at Honduras and Pakistan, we see almost double. You need the sample size of almost double. Less so for the other countries, Bangladesh, Laos, and Madagascar, Malawi. But importantly, if we look at the compartment bag test, the range is anywhere from 0 to 30% increase. So the compartment bag test basically performs and buys you a lot more power, that added category in that test compared to the 3-category test, or the 2-category test gives you a lot more power in your testing. But interestingly, when we looked at the 3 countries with better water quality, low precision methods performed either comparably or actually required less sample size. And so really the context of your site, the distribution of water quality is going to matter a lot with respect to the statistical power you have with those, with the different type methods that you're going to use in analyzing data. So this just is comparing, since there's a lot of reasons why you might choose a lower cost method versus the higher cost method. The last rate, precision is really what we looked at and analyzed in detail with respect to the statistical power. But you wanted to summarize just the cost of the equipment, cost of the consumables, whether or not you need a lab setting or a skilled lab personnel. So another benefit of these lower precision methods that we're calling lower precision methods is that doesn't require a lab setting, doesn't require the skill level that it does for the IDEX or membrane filtration. The equipment cost is much, much higher also. So there's a lot of advantages beyond just the statistical power issue that I just presented to you. So in conclusion, it looks as though that these low precision methods can reliably infer associations, and they may require moderate increase in sample size, but that's going to depend on context. And it also depends on how many categories that you're able to get out of your method. So again, the compartment bag method with 4 categories performs a whole lot better than having just 2 or 3 categories. And then I just wanted to emphasize this one other point with respect to being able to measure the higher concentration levels. So many of these methods provide a means to actually measure higher, get a lot more fidelity in the higher concentration area, higher contamination areas, which is really where a lot of the risk, you were realizing a lot of risk. So it's arguably, from a risk assessment perspective, much more important to be able to have fidelity in the higher end, which these lower precision methods allow, than in the lower end, where the risk is going to be comparably lower. So with that, just want to acknowledge our funder, NIH, and different collaborators from different institutions, including our collaborating institution in Ecuador and the University of San Francisco de Quito. So, thank you.
Questions for Dr. Joseph?
Thank you for a very interesting presentation. So I have questions. I have thought, so if you want have high precision, but also want to reduce the cost, so I'm thinking maybe you can reduce some sample size, but use some modeling to imputate a part of data set. Do you think that's a feasible measure to do that?
Yeah, but anytime you're going to use a model, you're going to have assumptions to the model. So I think that the theme here is that when you go from continuous to categorical, you're losing information. And yes, you can make assumptions, but I think the point here is that it's diminishing returns. Like if you can have enough categories, and I would argue that just the compartment bag method with just 4 categories is you're losing a minimal amount of information. And in fact, again, you're gaining more information at the higher concentration levels from a statistical perspective, which wouldn't even necessarily, you wouldn't necessarily need to do any kind of imputation and such, which is definitely doable, but has its own set of assumptions.
Okay.
Other questions?
I have a question. I think the use case you used here focused on drinking water quality. Have you replicated this looking for other contexts, so maybe like surface water quality based off of the EPA threshold guidelines for?
Right, no, we haven't done that, but that's a great idea.
Other questions? Yeah, great. Thank you so much, Dr. for Great, that concludes this afternoon's verbal presentations for this room. We'll see you all at the poster session up next. Thanks. Charlotte, I think I have your USB.
Yes.
Yeah.
I have
Thank you. Thank you very much.
Can we send Simultaneous multiple times?
Yeah, no, so, I I'd like to, I mean, I'd like to start grad school, maybe even a PhD, but Yeah, it's just, I also, I kind of enjoy the consulting work. So it's like, you know, it's like, which would I rather do? I mean, I think there's great.
But that's so you're working with assistant producer right now. So you're trying to get
So, I did it here at UNC, and the reason so I started this work, I just graduated in May, and I started my honors in 2 months.
Yeah, he's actually.
So during my senior year, I wanted to do an honors thesis, and I don't know if you got it from so I was doing it with him, and kind of plugged in with Dr. Fisher and the assistant
So we're also proud right
and all that. So
now.
yeah, so I was already in the department, and I wanted to do an honors thesis in the department.
That's so fun. Just for standard.
So you're a master's right now?
yeah, just my master. But it is my first semester.
Okay.
Yeah.
Where'd you do undergrad?
So undergrad was marine science. Okay, and then I went to science.
Okay.
Yeah.
Thanks for all that intro.
Thank
Okay.
you.
Did you do any?
I like the difference.
Did you go straight from undergrad to master's?
Yeah.
Did you work?
Quantitative.
I took one
And then I'll follow
like
up with
part-time job before, but 1 year I was working
yeah, see, and then
company.
try to get some of this.
Oh, okay.
Korean companies.
Yeah, so you have like you have a direct.
We have a draft.
So related to
Is everyone else, by the way, kind of
stuff,
out of the picture?
I think maybe I think they all want to leave, they want someone to.
Layla, I guess.
Okay, nice.
But I also work in private before.
Okay, yeah, so, yeah, actually,
It's kind of interesting, right?
yeah, I'm working, that's where I work in DC right now.
Ah,
mostly.
DC,
So
okay,
it's
DC.
in some in.
I don't think,
Maryland.
yeah, that's just me, I don't think you're that far away.
Okay, yeah, I live on the Virginia side.
Okay.
But yeah, it's
And I think that's
way different from here.
Yeah, I think
Yeah.
with the
Very,
very
I'm
little amount
from
of
North
time.
Carolina, so
Oh,
moving up
in
there.
native here, right?
I know,
Chuck
the work,
recently
but it's been,
reviewed
you know, the work's been cool.
Yeah, so I saw your systematic gradient continue. You see, it's not, if you get a lot of data sets, right? And then you can see the patterns, the periodical spikes maybe. So you can continue for another research using geostatistical spatial temporal analysis.
Okay.
Yeah, that's why, you know, the guy asking what is the paper?
Not on the text, in the text.
Not yet.
Yeah, I bet you we could crank that out, but I think you just, you know, in a paper, there's specific places you want to
or decision
you want it very, very, very briefly in
concentrations
the abstract,
of
you know,
one
text, and then you want it somewhere in
one
the
thing, for
introduction.
example, so they usually in UNC, maybe in master's student operation, geostatistical and spatial temporal analysis. So a lot of things to
Yeah, this is Christy, this is mine.
Okay, cool. Yeah. Okay, yeah.
So you will know how to map it, right? And then, for example, if we learn about horsepower, for example,
No, okay. Which is,
so if we connect spatial temporal and geostatistical analysis, right? So we can see the map in which year, for example,
I could put something
in
on.
which year
Yes,
each
and I'm
month.
coming back for this.
So the concentration is fine, right? So that's very interesting if you do that for years.
Yeah, I mean, yeah, it's something I like definitely, I've never, don't know much about.